Before I start, I guess there'll be time for thanks later on, but I do want to thank Dror and Erez for all the work they did in the organization, and the of course the Institute for Advanced Study. But very importantly, I wanted to mention the Gordon and Betty Moore Foundation that made possible support of student travel and expenses. So. All right, so this morning, from what I understand, Erez talked about Majorana at the ends of wires and at the edges of superconductors. So that's, of course, a very popular area of research these days related to topology. But this afternoon, I want to talk about topology of a different sort. And the terminology historically has become very confused, but I think there is some agreement on what the right terminology is today. So I'm going to talk about topological order, and that's a very specific phrase. And topological order here refers to, I'll stick to 2 dimensions, systems that have excitations with non-trivial anionic character and degeneracy on closed manifolds. Now, in fact, the materials that Erez talked about this morning are not of that type. So the things that do have topological order are spin liquids, fractional quantum Hall states, but topological insulators do not have topological order. Okay, so if you understand that, by the end of the school, we will achieve something. Did I make any wrong statements, Erez?
Roughly consistent, and that's a miracle.
Okay, so I'm going to talk about topological order. What my purpose today is to introduce it in the simplest possible context and give you some idea of how it appears and why it's a useful thing. When I first learned about it, it all had to do with degeneracies on, but if you put your system on a torus or put it on a sphere, different things happen. I said, well, who cares? Why should that be important? You're never going to do that in an experiment. But it is very important, as I will hopefully convince you, because it teaches you many other things that you can experimentally measure. Okay, so in one way or the other, everything I talked about is motivated by the cuprate superconductor. So let me just flash the phase diagram. But for today's lecture, let me just talk about the insulating material, which is an antiferromagnet. And in the real world, that material, in fact, is ordered, meaning there's a Hamiltonian for spin and a half particles on the square lattice. These are the copper sites in the cuprate superconductors. And to a very good approximation, it's just nearest neighbor exchange. So that's a very simple model, which we now know a great deal about. In particular, we know both from theory and experiment that the ground state has a broken symmetry. It breaks spin rotation symmetry by the spins forming this checkerboard pattern. They pick some common orientation modulo the staggering on the 2 sublattices. Okay, so this is, we'll say more about this later, but this is not the topic of this lecture. So this is a state which is, we would say today, it's a conventional state, or some people may even call it a trivial state. It has a broken symmetry, and once you know the broken symmetry, that tells you, everything you need to know about the low energy thermodynamics and the excitations. So in this case, there are Goldstone modes, spin waves that have been measured. The spin waves interact very strongly at finite temperature. That's because of special features of 2 dimensions, and all of that is also extremely well understood. But what I want to talk about is another possible state, which called the resonating valence bond state in the early days. In fact, the proposal goes back to Linus Pauling in 1949, where he proposed this state as a theory of metals. He didn't believe Bloch's theorem. So this was, but the correct context for this was given by Anderson, where he argued that this should be a possible state for a mod insulator. So this was Anderson's or Pauling's wave function. You imagine the spins, instead of being polarized in a definite direction, form spin singlets, and so each ellipse here represents a singlet. And then these singlets all resonate with each other. So just like in benzene, they resonate, but now there's an infinite number of possibilities of different ways of resonating. So this is superposition of all these configurations then defines the ground state. What we know today was this proposal really was the first proposal of what we would call a topological quantum field theory. This is described by a topological quantum field theory. There's certain essential aspects of it, and that's kind of what I want to get across today in some simple language. Okay, so what is topological about it? So the simplest way to think about it, simplest way to see something topological is imagine, as I said, put the thing on a torus, and then just draw a line on the torus and just measure the number of bonds that cross that line. So if I take this particular state, that's the line that I just drew. I see there are 4 bonds crossing this line. And then I take all possible local rearrangements of these bonds. So there's another one, there's still 4, now there's 2, and then there's 0. But you can convince yourself from a local rearrangement, there'll never be an odd number. There'll always be even. There'll always be an even number of bonds crossing any fixed line from all local rearrangements of these bonds, as long as each spin is paired up with something else. So this, yeah. Well, I'll show you a global one, and you'll see what's local. So everything that's not global is local. Something, imagine a very big torus, and I'm only having some short-range interactions, say within 10 lattice spacings or something, and don't allow anything that goes all the way around the torus. So to really change the parity of the number of bonds crossing this line, you have to do a global move, which I'll show you in a minute. Okay. So this is, in a word, the topological order. And this turns out, now of course this is a trial wave function, and it's an approximate wave function. We don't even know how to superpose these things. So it's not clear that there is something important for other physics, and what is this? It's not an autoparameter, but it's some quantum number that we can measure that characterizes the system on the torus. Now one thing you can see from this picture is also that there's another set of configuration I could imagine where the number of dimers crossing this particular line was odd. So to really know whether I'm in the odd sector or the even sector, I have to go all the way around the torus and count every bond. And if you give me a random wave function, maybe I find it's odd, then I'm sure that in every other component of your wave function, if it's good eigenstate of the Hamiltonian, will also be odd. So therefore, I can just see from this argument, imagining that only somehow the energy is determined locally, that there is a ground state degeneracy on the torus. There's the odd wave function, there's the even wave function. They almost have exactly the same energy. And that's true for a cut that you draw this way, but you can also draw a cut the other way. So you get a 4-fold degeneracy. So now you find, just from this very simple counting argument and lots of hand waving, that there seems to be extra states that you can create when you put the system on a torus that have almost exactly the same energy. All right. So that statement I want to, of course, substantiate by actual calculations and show you how this all really works out. Okay, so here's just a little bit of terminology that quantifies what I've just said. So for each pair of sites, I can introduce now a pseudospin, where if there's a dimer, I call it -1. If there's no dimer between these two sites, I call it +1. So now starting from each site, in this picture, each site has exactly one dimer coming out of it. So I take the product of the tau z on these 4 links, and I have to get -1, because there's only one of them that's minus. That's why I chose this to be minus. So there's a local constraint, an odd dimer constraint on every site. And I can also write down this conserved topological charge, this odd or even number, as just the product of tau z's along that cut this link. So WC is this product of tau z, it's plus or minus 1. And depending on whether WC is plus or minus 1, I have different ground states of my Hamiltonian. Yes?
Are you assuming dimer is only on the nearest neighbors?
No. As you can see from the pictures, I'm not.
So how do you define a tau z?
Oh, yeah, okay. Yeah, you can do it on that bond too, sure. Do it on every pair. Yeah. Right.
Hamiltonian.
Sorry, what? The what?
But you have this background
Oh, do you ignore that? That's the Hamiltonian, if you will. That's just a picture. Yeah, but the wave function is, this is all just a picture. I'm going to make this much more real soon. Yes. Yeah. Okay. There. Yeah. So really, as I was corrected, I really need to take. Let's say I only have nearest neighbor and first neighbor bond, second neighbor bond. That's all. Let me restrict to those. I don't want exactly nearest neighbors because that doesn't quite work for this lattice. That's just a technical thing we'll see by the end of next lecture maybe. If you just take only nearest neighbor on the square lattice, that in fact is not topologically ordered. But if you have second neighbor, that's enough. So let's take, so there's, then you're right, there's coming out of each side, there's eight tau z's coming out. Let's put tau z's on each cross bond also. Then my pictures are okay. Okay, then I have to remove this one, but all right. Yeah.
Yeah, okay. For me, it's not kind of obvious that that number of cross links is always, for instance, even or odd for
Yes.
each cross section. How to show it?
No, you pick one line. For that, now I'm not going to move this line. I'm going to keep that line fixed. I'm not going to move that line.
Yeah,
For that line, every state, every component of my wave function will have even or odd, assuming that the wave function is just related by local moves.
yeah, but what kind of operations you allow to change your link?
I'll show you 1 minute what kind of operation needed to change the parity. But really, roughly, the point is that, if there's a guy here, any spin here, it either has a partner on this side or has a partner on that side. Now, any kind of rearrangement is going to take either rearrangement on this side, or one will have to partner here, and then its partner on this side will have to partner there. So there's just no way you can remove an odd number. You just think about it a little bit. That's all. Okay. Right. So now how do I get an operation that changes WC? So here's how I do it. So here WC is 2 here. So let me draw a line C prime, which goes from side to side, but it goes from in this way. It goes empty dimer, empty dimer, empty dimer, and goes all the way across. Okay. So on this contour C prime, I now introduce this operator VC, which is tau x. So it's going to just change the value of tau z. If tau z is -1, it becomes +1. Okay, so if I apply VC on this, and this I do all the way globally, then what will happen is that what was empty becomes filled, what was filled becomes empty, and it goes all the way around. And now you see I have WC is -1. So VC is an operator, at least for this configuration, it's an operator that will flip the value of WC, and it has to wind all the way around the other cycle of the torus. Okay, so I have to really do something globally, move everything over 1, and then I will change the value of WC. And anything that doesn't involve this kind of global cycle will not change the value of WC. Okay. So what we know now is that we should really think of these operators, WC and VC, as operators that act on this 4-fold degenerate subspace. There's, of course, different VCs I can define for different contours. And what we learned from field theory, this is what I try to show you, that those VCs are all roughly equal to each other. But ignoring those subtleties, you can already now see an important property between WC and VC, which is that, I hope I got this right. Did I make a mistake somewhere? Oh yeah, no, I'm okay.
Your
Yeah.
sites, they don't have connections outside this VC. Is it always the case?
Well, for each C prime, I can define the operator V. And so I picked one C prime. And it's certainly true that this operator will flip the value of WC.
All sites on this contour, they are connected just only to other sites on this contour. They are connected to some.
Yeah, that's how I chose C prime. Right. So this is at this point, this is an approximate argument, and it's by no means a proof. But anyway, what you can see already now is that the red line and the green line only share one bond, which is this one, and therefore they anti-commute with each other because tau z anti-commutes with tau x. So I have this property, if I have a contour C here and a contour C prime here, that I can define 4 operators, WC, WC prime, VC, and VC prime, and these anti-commute in pairs. Okay, so I can just make these Pauli matrices. This is a different set of Pauli matrices, and so these are operators that act on the. So each Pauli matrix defines a 2x2 subspace. So I have Hilbert space of 4 sites, and these are operators that act on this 4-dimensional Hilbert space, and they obey these anti-commutation relations. So this is one way of characterizing very roughly, and this is not a proof at all. Of course, now we know that this is all essentially exact, and I'm going to try to show you from a field theoretical point of view where these relations come from. But just so they have an intuition, that's what this is meant to convey.
Do these tau live on sites or on links?
The tau lives on the links. Yes.
And but there can be more than 2 variants. There can be one singlet on this link. There can be different kind of situations when there is no dimer on this link.
Yeah, well, that's tau equals -1. So that's, we pick any pair of sites. If this is -1 when there's one dimer and it's +1 otherwise.
For any configuration,
Yeah,
which does not have a link on this bond.
that's right. It's always +1 in that case, correct. So that's difficult to show. WC does, obviously, but VC it's more difficult to show, right? Well, it's simply that Hamiltonian is local, so the global winding number shouldn't matter. Locally, you don't even know what the winding number is. So you expect the ground states to be approximately degenerate. And VC operator strictly is just the operator that takes you from one state to the other. The fact that it can be written as something along a single contour is not obvious. There's probably a fatter contour that you have to worry about. But at least I've shown you an example of an operator that will take you from one to the other. One component of the wave function, it just takes one component to the other component. It doesn't take the full wave function. That's more complicated. Yeah.
Can you show the next slide, please? Yes, this slide. So this C and C prime are of different type of contours. One cuts through the link,
Yeah,
the link,
correct.
and another one connects different sides.
Yeah.
So how can you define both WC and V?
Well, they define on the operators sit on the links. So that there's an operator here, operator here, operator here, and you just count them differently. Yeah.
So even these are 2 different paths.
Yeah.
We can still define.
Yeah, these are all the same links. The L is the same. So WC is, where is WC? Well, I didn't write it down, or maybe I wrote it down somewhere. Yeah, no, WC is on this link, is the same as this L. It's just that you count them differently. One crosses links, the other goes along links. Yeah. All right, so this is all food for thought before I launch into. So now, before I get into use the blackboard, there's a completely separate set of developments which happened coming from particle physics, where people were studying Chern-Simons gauge theories. And in particular, there's a very simple Chern-Simons gauge theory in which you can define operators that have exactly this algebra. And so this is the definition of it. So it's, I don't want to spend a lot of time on this because we'll come back and say more about it later. So there are 2 gauge fields which I call A1 and A2, but let me call it A and B. And this Lagrangian here is simply 1 over pi d dx dy dt times epsilon mu nu lambda a mu d nu b lambda. So there are 2 U1 gauge fields, and the Lagrangian is this. So now for Chern-Simons gauge series, it turns out that the dynamical degrees of freedom, you can always fix your gauge so that the dynamical degrees of freedom are AX, AY, BX, BY. And then this Lagrangian simply becomes 1 over pi dx dy dt times AX dot BY plus, well, I get all the signs wrong, but excuse me, BX dot AY or something like that. So what this tells you is that AX is canonically conjugate to B. So they have the usual commutation relations of P and Q. This is like PQ dot BX AY dot. So you can think of this as a Q and this as a P, or other way around, and similarly here. So you have two pairs of P's and Q's which have the usual Heisenberg commutation relations. And knowing those commutation relations, you can then take these Wilson loop operators, which are called VC and WC, which are then the line integrals. If you have a torus, again, I refer to this, then VC is the line integral of A along this loop, and WC will be the line integral of B along this loop. And then you can show just from the commutation relations and this factor of pi being carefully chosen that these Wilson loop operators obey exactly the same set of commutation relations. Okay, I should really explain this, but then I won't get anywhere. Sorry? Oh, sorry. Well, okay. It's almost time for me to raise the screen, so I'm going to raise the screen in a minute. Yeah, in fact, it is exactly time, so why not I just do that? Is this the left screen or the right screen? Oh, thank you. And then I turn the lights on. Okay. Sorry about that. Okay, so this is the Chern-Simons gauge theory with a factor of 1 over pi and two gauge fields A and B. And after a little bit of algebra and gauge fixing, you can write it this way as the AX dot BY and BX times AY dot. So AX is canonically conjugate to BY and BX is canonically conjugate to AY. So you know their commutation relation, and then from that you can work out the commutation relation of the Wilson loop operators, and then you find exactly the same commutation relation that I showed you explicitly from the WC and VC as I defined them. So this is done, worked out in many places in literature. I don't want to spend time on this because it's a bit, I'm not really going to use this Chern-Simons theory for anything, but it's useful to know that this is the topological quantum field theory that in modern language characterizes this resonating valence bond state. Okay, and of course there is since then Kitayev's beautiful toric chord solution where all of this is completely exact, and you can explicitly see what these operators are, and all the approximate statements are made actually become exact statements. Okay, so what I want to do today is to write down a Hamiltonian, which we are pretty confident displays this topological phase, but also show some of the other phases it displays, and try to understand something about the phase transition, the general structure of the phase diagram, and how that's constrained by all these principles of topological order and then also related symmetries. So let's just start with model of bosons on the square lattice. So I'll take some bosons. So just take the so-called Boson Hubbard model, which has, of course, now been seen in experiments. So we just take Hamiltonian is minus W, sum on, let's say, nearest neighbors, B dagger I, Bj, plus U, sum on I, Ni times Ni minus 1 over 2, where Ni is B dagger I, Bi. So at u equals 0, then these are just free bosons, and we're going to talk exclusively about 0 temperature. And if you have some density of bosons, they're going to Bose condense and form a superfluid. So I'm going to restrict myself for most of today's lecture to the integer constraint. So Ni is going to be equal to 1 on every site. So there's one boson per site on average, but you can get different phases that the system appears in. So in particular, if you look at the phase diagram as a function of u over w at this density, what's relatively easy to see that there has to be a phase transition at some critical value. And on this side, you have a superfluid. And on this side, you have an insulator. And anticipating things we're going to say later, this is what you'd call a trivial insulator. So in the superfluid, there's a Bose-Einstein condensate. So B has non-zero expectation value. And the insulator, usually actually doesn't appear. It appears only because you have exactly one boson per site. So when U is very large, there's an obvious state which becomes the ground state, which is not a superfluid. And that's the state where you have one boson on every site. And they stay apart from each other because U is so large. So you have one boson on every site, and that's the insulator. Okay. So what I want to get to, however, of course, so this is all very simple. What I want to do is now add further interactions on this model as defined, so that it has something else going on. In particular, I want to get a state. What I want to get to is describe a state which is an insulator, which is topologically non-trivial, in the sense of this lecture. Okay, so as I said, we know a lot about this. We also know that this critical point in 2 dimensions is described by relativistic quantum field theory. And that's a useful thing because many exact statements can then be made. And so let me just state it. So there's a field theory here for the critical point and its vicinity, which is has the Lagrangian d3x of grad psi squared plus let's call it s psi squared plus u psi to the 4th. So S is something that S increases this way. So when S is very large, then psi fluctuates about 0. And fluctuation of psi is basically some continuum limit of the boson. So when psi fluctuates about 0, you have an insulator. And when S is negative, then you have the famous Mexican hat potential. So V of psi. It looks like this for the insulator. This is psi, and looks like this for the superfluid. And so when you have this Mexican hat, then psi condenses at one point on this circle, and that's what gives you superfluidity. Okay. So I don't want to spend a great deal of time deriving this. It's in many places, including a good book I know. And so that's a reading assignment if you want to learn more about the details. I guess so what are some of the non-trivial features of this? This should be not just grad, this is in relativistic notation, both space and time. So one important feature of this is that once you have relativistic theory of this type, it's particle hole symmetric. That means excitations when you add particles have the same energy as excitation when you remove particles.
Is there any reason you don't keep the 6th order term?
Well, it's irrelevant in, okay. So this is a 2 plus 1 dimensions, and
so 6, 5 to the 6 is marginal.
Well, okay. It's marginal in 4 dimensions, but I guess once you put the anomalous dimension, it's not exactly marginal. There's 2, okay. I'm going to be very sloppy about critical phenomena on the whole. What was I going to say? Oh yeah, it's particle-hole symmetric. So what that means is that the density and excitations of particles are the same as that of holes. So in this insulator, for example, I can imagine creating a hole here. So this is now an empty site, and putting that particle over there. So this is a particle excitation, this is a hole excitation. And you can see they must be in equal density, because the number of holes must equal the number of particles, because there's exactly one particle on every side. So this constraint is absolutely crucial for getting the relativistic structure. Only then the particle and the hole have some symmetry. Now, there are higher order terms that break the particle symmetry, but they turn out to be irrelevant near the critical point. Okay. And you can also see here that even the existence of the insulator requires commensurate density, because suppose you had one less particle than number of sites, now this particle can move. So, or another way of thinking about this, hole can move freely. So the system becomes a dilute gas of bosonic holes, which will then condense. So it's always a superfluid unless n is exactly 1, unless you break the symmetry. Okay. All right, so that's just a review of some standard terminology, which I want to use to then finally derive this topological quantum field theory for a different model. Now I'm not sure. Yeah, okay, let's just leave that there. I'm going to come back to it. So this is, relatively boring phase diagram. So I want to add now some other terms to the Hamiltonian. And I think I'll go back to can I get the screen down now, please? Okay, so here's the Hamiltonian, which is considered in different forms by various people over the years, but the form I'm using is due to Lasik, Motrnik, and Senthil. All right, so I already told you about this. Oh, sorry, it doesn't even have that term. Okay. So I told you about the Boson Hubbard model, these are the bosons B that I just told you about, now labeled by R and R prime. Sorry about that. And they were hopping on this bigger lattice with the large circles. But now, so this is the way they stated it, but it's not essential to think of it this way. Imagine that the boson can also sit on the bond. So the boson can hop from here to there, and then it can also hop from here to there. So that's W1 and W2, just ordinary boson hopping terms. So a slightly extended model where I put in another state for the boson to occupy on the lattice. Now you can think of this extra as an actual state, or it's also perfectly okay to think of it as a boson hopping back and forth between the two sites. So you can think of this either as the same boson. Let's go back here. You can think of this psi particle here as actually a boson sitting there, or you can also think of it as a boson that's going back and forth. It's in the bonding orbital of these two sites. It's just a matter of taste. If you don't want to put imagine there's actually a boson there, well then just imagine there's a state where the boson is in some linear superposition, coherent superposition of those two sites. All right, so that's kind of a trivial thing, it's just changing band structure. This interaction we already have. This is also some local repulsion of bosons on this side. So the crucial new interaction I want to put in, which now is called capital U, this is the little u I had before, is this thing. So this is a more extended interaction. It's not completely on site. And the crucial feature of this is it's like a repulsion between bosons in this neighborhood. And so you can think of this boson here as half belonging to this side and half belonging to that side. So if you want some energy that counts the number of bosons in this neighborhood, you take the number of bosons here plus half the boson here plus half the boson here plus half the boson there plus half the boson there. And that's what this measures up with an extra overall factor of 2. Okay, so this is just some operator that will commute with the Hamiltonian, and it's a slightly extended interaction between the bosons. Okay? Yes? Okay, it's just some boson that sits here. Let's say if you want to be perfectly definite, this is the Hamiltonian. B and psi are just boson operators. Huh?
Are they different? Or,
Okay, for this slide, they're different. So it's a matter of taste, but I guess I'm confusing you. So let's imagine that this is just a different lattice. So my cold atom friends make this lattice. Boson can sit here or here or here or here. That's it. But the hard thing for them to do, at least in existing experiments, would be to put this repulsive interaction that involves these 5 sites. Okay, so it's a slightly extended interaction. I mean, this is, of course, cooked up to make things work out nicely, but in the end, the phases we get, we think, are more robust and should be present in many other models. But this is a model by which you can really analyze things. This one? Yes. You can make it anything you want. I mean, but then we want to prove things as. So this is just. Yeah. Well, as we'll see, the physics has to do with the existence or not of topological order. What we want to do is come up with a criterion for that. Okay. So it turns out this is the more complicated phase diagram in this case, where you have exactly 1 boson per site. This n sub r has a 2 because, again, there's an extra overall factor of 2 the way Senthil et al. Defined it. I would have defined without the factor of 2, but that's the way it is. So I just cut and paste their equations. I was lazy. So sorry about that. Okay, so this is their phase diagram. What I just told you about the superfluid and the mod insulator is down here at small u. And then it turns out at large u, and there's numerical studies to prove it, there's another insulator that appears here. And this is the insulator which they call fractionalized, which will have topological order. And now you have this remarkable phenomenon that you have 2 phases, one phase here and one phase here, which have the same symmetries. That is, if according to the Landau criterion, there's no broken symmetry in every one in both of them. But this one has this extra degeneracy on a torus, which sounds like a really boring thing. But what that tells you is that you cannot continuously connect this insulator to that insulator. There must be a phase transition between them. In this case, it turns out to be a second order phase transition. So that's something very physical. You can measure that in the experiment. Here's a gapless line. So what you know that there must be a gapless line separating this phase and this. And the reason you know that is because you understand this topological structure. So then there's a very measurable consequence of this kind of abstract feature of this insulating state. All right, so what is that? Oh, no, I'll come back to. Yeah, so this I've already talked about, sorry. This phase transition was this O2 means the O2 symmetry Wilson-Fisher field theory that I just wrote down. And what time do I end? I don't know. Hopefully by the end of this I'll tell you what the other phase transition also are. Okay, so here's the trivial insulator again, where you have 1 boson on every site. And now imagine I start these things fluctuating. So what I've done here, I've taken the boson that was here and put it on the W. That's one way to think of it. So think of this ellipse as a boson sitting on the W. Or you can think of it, there's no W, W is fake, and this ellipse is this bounding orbital of the boson working factor. So in this state, there's 1 boson is sitting here, and a second boson is going back and forth, okay, in the symmetric combination. All right, so this is some excitation of the trivial insulator, and now I start doing this more and more everywhere. And eventually, I put everything on the bonds, and at some point, of course, these pictures are approximate, but at some precise point, something changes, and I get a state with topological order. And certainly, if I think in terms of the bonds, again, here it's again obvious. I just draw a line, and then if I only have bonds allowed, then I can see that the number of bonds crossing that line is conserved modulo 2, and therefore this may be a state that has topological order. Okay. Yeah, in this case it's nearest neighbor dimer, but there's 2 dimers coming out of each side. It's you'd call this an even dimer model.
If you can just break a dimer and just put your boson on the side.
You can.
So how is it conserved? Remember?
Well, okay, so that's right. So provided you don't allow sites, it's conserved, right? So we want to. You're right. So this is an approximate picture. We want to make this have a real theory for what is this topological order. Okay. All right. So let me now show you how you get a theory, and how do you really make the whole idea of topological or precise, and how do you know what the phase transitions are? Do they even exist in what is the universality class? So what we're going to do is take the limit and go back to this Hamiltonian. Take the limit where u goes to infinity. Okay, so if u is strictly infinite, that means we don't allow fluctuations in this number operator. And in that limit, one can really show how topological order appears. So we take u, capital U going to infinity, and we're going to conserve the number of bosons on each diamond, where the edges count for half and the center counts for 1. All right, so if that is really the case, what are the kind of moves that are allowed? So let's go back, and then you can sort of see that here. All right, so I can't write. I guess I will need better to have an extra board. All right, I should have drawn on the picture. So let me try to do this on the fly. Okay, so what is this operator here? So we need an operator that conserves this NR on every site, capital NR. So if no, I really need to do this on the board, sorry. So let's look at that thing. So there's a bond here. Say you have a boson here and a boson here. And then what happens is that these 2 bosons both sit in the center. So they both go here. So now if I look at this particular diamond, I don't know what's happening elsewhere. What's happened is this has gone over there. So this boson count has decreased by 1, but really it's gone there, so it's increased by 1/2. And then you take the second one and put it here, it's also increased by 1/2. So I've conserved the value of n on this diamond, and conversely on that one too. So this is one of the simplest allowed moves. Now, of course, the Hamiltonian doesn't have this, but it's virtually generated just the way super exchange interaction is generated in the Hubbard model. So the J bond, will be something of order W squared over U, where 2 bosons on the edge both come to the center. That conserves this NR. And then there's another operator that also conserves NR. That involves a plaquette. And it's like an exchange term where 2 bosons move together. Where is the eraser gone? Oh, it's back there. So here's a plaquette. And say I had 2 bosons here, 1 boson here and 1 boson here. Then what can happen is that they can move to here to here. So this process has amplitude K ring. And again, you can see that the number of bosons on each of these diamonds as measured by NR is conserved. So these are really the only simple local moves that will preserve the value of NR when U is infinity. Okay, so now we have this particular Hamiltonian for bosons, and this the same. These are bosons sitting on the bond or on the links, and this particular Hamiltonian has the feature that no boson can move on its own. So we're describing some insulating phase. So boson can't move on its own, so it can't possibly condense. They can only move in pairs, and the pairs of terms are like this: 2 bosons can go from an end of a link to the center, or two bosons in a ring can move around. That's it. Okay? And the density of bosons on each side is 1. All right. Now, it takes a little bit of algebra, which maybe I'll do on the board in a minute, to show you that this is, in fact, equivalent in some limit to a gauge theory. It can be rewritten as exactly as a gauge theory, which almost has a relativistic form of a charged 2 Higgs scalar and a compact U1 gauge field. Okay, this is just rewriting this Hamiltonian modulo some minor changes. Okay, so let me try to show you how that happens. Yeah, this I should really use the board or prepare notes. Sorry. By the way, any questions so far? All right, so can you raise the screen, please? Let me show you on the board. All right. So one of the moves that I showed you was this particular, the simplest move was I had boson here and a boson here, and they would go to a boson sitting here, both of them sitting here. Okay, so what I need to describe this move is, let me call this site 1, this is site 2, and let's call this site 3. So the move is B1, B2, and then psi 3 dagger, psi 3 dagger. Now I'm going to make the approximation of representing the bosons by a phase factor. So that's what I'll call e to the I phi 1. And this is, now I'm going to use the factor on a square lattice. So on one sublattice, I'll call the boson operator e to the I phi 1. And on the other sublattice, B2, I'll call it e to the minus I phi 2. That's just a choice of definition of the phase phi. And this psi 3, I'll call as e to the I A3. Okay, so now when I plug this in here, this term here plus its Hermitian conjugate is the same as cosine of up to sines phi 1 minus phi 2 minus 2A3. Okay. So the minus sign was chosen because that's to make this have this very suggestive form. So this I'm going to view as sort of a gradient. So I'm going to write this as cosine of dx phi I minus 2aix. And here the notation is that dx of any function of I is the same as f of I plus x minus f of I. So it's a discrete derivative in the x direction. And so this is phi 2 minus phi 1, which is, this is the side I. You go forward in the x direction, and you get the gradient. And then we think of the phase of this psi field sitting here as a spatial component of a vector potential. So in this form, what we see now is that there's an obvious gauge invariance. I can take phi I goes to phi I plus any lambda I, and aix goes to aix minus dx lambda I. There's a factor of 2 here because that's charge 2. And you can see the whole thing is invariant under there. So now there's a gauge invariance that's built into the structure, and really that shouldn't be a surprise. There's a gauge invariance because you have a constraint. You have a constraint on every site that n sub r on this diamond is fixed. And since that number doesn't move, there's an infinite number of conservation laws. And associated with those infinite number of conservation laws are an infinite number of symmetries, which are these gauge transformations. Okay.
And what are the commutation relations for phis?
Phis all commute with each other. There's a conjugate variable, the number operator. So there'll be a number operator and phi, and the commutator will be I, something like that. So n is this number operator here. Okay, so we're just representing the boson by a phase, which is, and the number operator is the angular momentum associated with that phase. Sorry?
Why exactly does it come out to be a compact phase?
It's always compact. Again, the n equals 1 is important to make it relativistic. So that's the time derivative term, which I am not showing you. For them to work out correctly, you have to have exactly one boson per site, or any integer number would do.
What motivates the choice of these two different sublattice structures?
Otherwise it'll be the phi 1 plus phi 2 if you didn't have the staggering. So for this construction to work in this model, you do need this to be on a square lattice. Where you call bosons on one side has charge plus 1, bosons on the other side have charge minus 1. Otherwise, it doesn't look like a gauge theory. It doesn't look like a familiar gauge theory anyway. Okay. Then the other term here, the ring term, that gives you the compact gauge theory structure. So the ring term now this will be a test of my remembering the signs. So you had bosons that were here, and then they end up over here. So this, let's call this A1, A2, the Bose operator is e to the I A1, e to the I A2, e to the I A3, e to the I A4. So if you just write this out naively, this will give you the term where this moves over there, will give you cosine of A1 plus A3 minus A2 minus A4. Okay, now let me put a bar on every one of these. So everyone okay with this? Now this doesn't quite look like the curl of a vector field. We want to make this look like a curl of a vector field. And you can do that by changing the sign of it. What you want, this minus this. So, you want this minus this plus this minus that. So this you can then write this. So now if I define A3 is equal to, again, change the sign on this lattice, and then you also, maybe this one, I don't remember. So again, this you have to look up the original papers to get all the signs right. I'm sorry, I didn't get it right on the board. So if you define it this way and keep the other ones the same, this in the end can be written as cosine of epsilon alpha beta del alpha a beta, where alpha and beta are x and y. Sorry?
What do bars denote?
Bars are just written here. Sorry, I'm sorry. There should be I want to change the sign of A3 and I want to change the sign of A4. And for the others, I don't change the sign. So when I get rid of the bars, this ends up looking like a curl. What I want it to look like is, okay, sorry, I should slow down, do this again. Let me try carefully. So what I want here is a term that looks something like this. So let's call this A1, A2, A3, A4. What I want is a term which is cosine of A1 plus A2 plus A3 plus A4. I want to give this A a link, an orientation, and I want to get the curl of the cosines this way. Now what are the psi operators? So if I define psi here is e to the I A1, well, this is going to come with the same sign as this one. So really, right, okay, which if I orient this way, this psi would be e to the I A1, this psi would be e to the I A3, but these have to come with the opposite sign, e to the minus IA2, psi is e to the minus IA4. So you choose the signs carefully with some sublattice staggering. So what you get is the cosine of the curl. And you think of A as a vector field where the A going this way has the opposite sign from the A going the other way. So there's a way to do that. Sorry, I didn't get this completely correct. Consistently, so that in the end, your final action looks exactly like a compact lattice gauge theory, where you have a gauge field A mu and a phase phi, and the phase has a charge 2 with respect to this gauge field. So let me just write that down for completeness then. So the final Hamiltonian you're dealing with looks something like this. It has some minus, what is it, j, somewhat cosine of d mu, d alpha phi I, minus 2 a I alpha, minus k of cosine of epsilon alpha beta, del alpha a I beta. And then you have the conjugate terms for sum on I ni squared. And then you can also get sum on I alpha, and these are n psi I squared. Something like that. Anyway, so the degrees of freedom are phases that sit on the sites and the links, and their conjugate number densities. And this is the field theory that we're going to work with.
So
Yes?
Is it different from just a collection of Johnson junctions?
You can view that way, yes. So you could build this using connection of Josephson junctions, yes. The hard part again is having that 4-body term that projects you down to the subspace where you're going to get this fractionalized state. All right, so I'm going to skip ahead then and rewrite this in a form that particle theorists would love. So now I take this particular lattice gauge theory and do exactly what I did for the boson model. I wrote the boson model as a relativistic field theory. I'm going to do the same thing over here. So at the end of the day, so in some continuum limit, which may or may not work, but let me just write it out. So I can define a field where I'm going to call this field phi will be e to the I phi I, and A just becomes A in the continuum. So then my theory would be, Lagrangian would be d mu minus 2I A mu times field phi squared plus some S mod phi squared plus U mod phi to the 4th. And I can just take the continuum limit of this cosine, and that will be epsilon mu nu lambda del nu a lambda whole squared. Okay. So in this language, this looks like a Higgs field, just like the Higgs field in the Weinberg-Salam model. It's a U1 Higgs field, and has charge 2 with respect to a certain gauge field. Now the charge 2, you might think when I write it this way, can be scaled away, but it turns out to be very important because we have to remember that this cosine appeared in this way, and that determines the quantization of the monopoles. Anyway, that turns out to be important later on. Okay, any questions? All right, so what I've shown you is some way you can take a very ordinary looking boson model, take a certain strong coupling limit of the boson model, and out pops a gauge theory. And it's a gauge theory with some matter fields and also some gauge fields. And this is probably the most honest form of writing it out. All right, yes?
So just to understand the model in the beginning, so can I just think about it as like I have two orders that I'm kind of considering, and I'm putting both at like the psi order and like one is normally stable and then the other is just like
Yeah.
similar. So I'm just kind of writing the interactions between these two possible orders.
Right.
And then
Okay, so yeah, let me say that a little bit more completely. So I started out by talking about the superfluid and the insulating phase, the trivial insulator and the superfluid that you can get by just considering bosons moving on the lattice. Then I put in this non-local term and took the limit of very large U. And what I wanted to get a theory for an insulator, and this is my effective theory for the insulator. But this theory will turn out to have two phases. And we want to understand what those phases are. But this particular theory as written doesn't yet have the superfluid phase because I've taken the limit U goes to infinity. So this is a theory for the insulator at this point. Okay.
So the two orders, I mean, I take the valence bound state and the non, like the V's would correspond to the trivial insulator, and then the size would be the, if they.
Yeah, so there's one RVB-like state, and then there's the trivial state. This theory has both, and that's what I want to show you. Yeah.
So you have three models, if I understand correctly.
Okay, remind me what the three are.
The first one, which had the lattice with the spins that move with pies and size.
Yes, okay.
This is number two, which you derive from it, the lattice gauge theory.
Yes, correct.
And the third is the continuum.
Yeah, so focus on this one. This is the most important one that I'm going to play with. The continuum is not always valid. In fact, it's usually not valid. This is where we should start with.
So about this system, do you have a dynamical excitation with charge 1 under A or not?
That was going to be my next discussion. But in the insulating, no. So there is an excitation with charge 1 under A, but that has a gap, but it comes down when you
That's
go.
not included in this Hamiltonian.
Not yet. That was going to be the next slide. In fact, yeah.
Just something which I'm a bit confused about. So you have this non-local interaction, that's fine. But it wasn't clear to me through the sketch whether, sorry, whether the square lattice was important or any bi sort of effective lattice or any other fancy lattice that people like making.
I suspect we could make this work on honeycomb too, but bipartite nature is important. And yeah, let's just stick to the square. But for this particular model, the bipartite nature is important, at least to proceed with this analysis. The phases that we're going to discover could appear on any lattice at integer density. Yeah.
So this capital phi, is it the quantum limit of phi I or e to the phi I?
E to the phi I. Yeah. Okay. Let's see, how should I do this? Just one second. What's next? All right, well, let me just continue along the line. So could I have the screen back then? Yeah.
Even though we didn't answer it, I'd like to
Yeah.
ask it again.
Yes.
In the first version where you had only the pies and size,
Yes.
did you have their particle charge 1 or not?
In the original Hamiltonian, yes, absolutely.
But you don't have it here.
No, no. So I will show you. What you're calling charge 1, what you're calling charge 2, I call charge 1. What you're calling charge 1, I call charge a half. But it's just an overall nominal. So let me just go back and extend this model, and then I'll describe its phases. Okay, so this is the original Hamiltonian. These are bosons. These bosons I say has charge 1. Each boson has charge 1, and there's this constraint in the strong coupling limit where this number has to be 1 on every side. So in that limit, what I showed you was that this theory of bosons can be written in terms of this compact U1 gauge theory. So this is a U1 gauge theory here with compact because of the cosine term, and e to the IA and e to the I phi are operators that create bosons on the links or on the sides. Okay. All right. Now, but this theory, doesn't have any charge fluctuations because everything that we do involves conserving number of bosons on every diamond. So there's no fluctuation in the actual boson number. It's just rearrangement. It's all about rearrangements. And one consequence of that is that although it has this gauge symmetry, there's all these infinite number of local symmetries, it doesn't have any global symmetry. There's no global charge here at all, because the charge associated with shifting phi is completely absorbed into a gauge transformation. Okay. So to get a global symmetry, remember that the boson number can fluctuate. I have to really relax this constraint where I work only in this Hilbert space where n sub r on every diamond is 1. Okay, so how can we do that? So here's a configuration where I have a charge fluctuation. So on this site, let's see how many bosons I have on this diamond. So this counts for a half. This counts for a 1. So relative to the ground state where I had 1 on every side, I have an extra charge of 1/2 here. Pick any other side. So if I pick this side, this counts for a half, this counts for a half, I have 1. Here I have 1. Here I have half from here and half from here, I have 1. Similarly there. So every site has 1, except this has 1.5, and that has 0.5. So relative to the ground state, this configuration has a half charge excitation here and a half charge excitation over there. Okay, and so the topologically ordered phase, one way of just seeing what it is, it's a phase where these half charges can move freely. That will be the phase that will have topological order. So how do these half charges move? Well, that's very simple. You just, you take a boson that's sitting on the bond and you move it over there. Okay, when I do that, you notice this is perfectly happy. That doesn't have a half charge. The half charge has moved here. So there I had to remove a bond completely to move a half charge over. And then here I have to, there I added a bond. So I added a bond, and now you can see I have 1 here because there's 2 bonds coming out. But I have 3 bonds coming out, or extra charge 1/2 there, and so on. Now I remove the bond and moves there. And so, okay. So basically it's possible when I now relax the constraint of nr equals the same on every diamond to create these half charge excitations which can start moving around. So really and this is an excitation that carries real charge, and this is what I need to move around to get a Bose condensate. Otherwise there's no way I'm going to get a superfluid. So I need lots of these excitations. Now they can of course bind in pairs to create integer charges, but you can also have half charges moving around. So now I have to put in addition to this theory I just defined, put in the motion of these half charges. And so I introduce a field theta r, which is e to the I theta r, which creates a half charge. And its hopping is just this very simple term here. But you can see what you had to do to create, well, actually, so let's go back and see what happens when the hop. So for this thing to move, I just had to remove this bond. So what I really did, I just removed that bond. Now that removing that bond is precisely the operator e to the IA. And then when it moved further, I had to add a bond, and that would be again e to the IA on that bond, modulo a sign. And so really when I put all these operators in, the operator representing the motion of this half charge is just cosine of AI alpha. Just have to put a cosine term for every bond, and that will allow this half charge to move around. Now this looks like a very ugly term because I seem to have lost my gauge invariance. So I can restore my gauge invariance just by a gauge transformation and introduce another field theta. So that's what I've done here. You can think of theta as something I just put in by hand to restore gauge invariance. If you want, you can put theta equals 0, then you're in a gauge fixed theory. But you can sum over all values of theta, you're not going to do any damage because you can always absorb theta in the real definition of A. Okay, so I can continue to write down as a compact U1 gauge theory by introducing this matter field that carries charge 1 in this A field. So now I have, this is now the complete theory, and this is kind of the lattice gauge theory which has the same phases in the same phase diagram as this original Hamiltonian, this one over here. Okay. So of course U is not infinity now, U is finite. So I'm now allowing U to be finite. So in the limit of large U, when I now allow for charge excitation, I've argued that this simple boson model, very naive looking boson model, can be rewritten as a lattice gauge theory. And the lattice gauge theory has the following structure right here. It's called two matter fields, one with charge 2, the other with charge 1, and this Maxwell type term, which is the cosine of the curl of A. So in fact, you could think of this now defined on a space-time lattice, on a cubic lattice. So this is a stat-mech model defined on a cubic lattice, where the degrees of freedom are 2 phases on each side and 1 phase on every link. And this is the action. It has lots of symmetries, and you can now put this on a computer and simulate it. It's a perfectly positive action, and that's our gauge theory. It's got 2 types of matter fields and 1 compact U1 gauge symmetry. Yes?
Just to be clear again, this first term, you just put it phenomenologically by saying these are the possible excitations, or you can do it just by analyzing, say, like one particle excitations above them?
Yeah, so you could do it, right. And so it's the leading term. If you want to put charged excitation, and this is the first term that will come out, just looking at the band of charge excitation would be just cosine of A alpha. Right. Yeah.
In the topologically ordered state, you have a freely propagating matter field.
Yes, and that would be the theta,
Why
right.
do you call it insulating?
Well, okay. Sorry, no, you're right. So there is it's freely propagating, but it's gapped. It's not confined. It's allowed to propagate, but it's an insulator. Sorry?
The gap is the U.
Yes, right.
So,
Yeah,
to ask my question.
sure.
So, which, the original Hamiltonian that you wrote, is it this equivalent to this one?
Yes.
Or is it equivalent to the previous one?
It's equivalent to this one.
This one?
Yes,
The one which had only 2 terms is incomplete, you have to add.
that's right. Now you can get the superfluid phase 2 out of this. All right, so yeah, I guess now I'm learning. I'd like to go back and forth between the board and the slide. Next time I'll have a blackboard there or something. Actually, most of the rest of my lectures are not on slides, so it won't be this inconvenient. Okay, so could I raise the screen now? Let me just do it on the, yeah. I think I'll try to do the rest on the board, on my animation. Okay. Sorry? Yeah. Yeah, sure, there are. There are composites of these. I just, at this point, I'm doing, qualitative arguments. Okay, so I don't know what happened there. Okay. All right. Yeah. Okay. All right, so okay, now I can do it. Okay, so I have the following type theory of minus cosine of d mu theta minus a I mu. Then I have minus j cosine of d mu phi minus 2 a I mu minus k of cosine of del cross a. Okay. So now I can talk about various possible phases in this phase diagram. Now, what easiest way to think about it, actually, sorry, I'm just going to look this up and then tell you how the phases work. Okay. Okay. So let me try to draw let's see. Okay. So there were these three phases that were in Senthal's phase diagram. Let me just draw them up again, something like this. So this was the superfluid. Then there was the insulator, trivial insulator. And there's this phase here, which we'll see is non-trivial or topological insulator. No, I shouldn't call it topological insulator. Insulator with topological order. Okay. So you can actually understand these just simply by thinking about what's condensed where. All right. So you can imagine a phase where these half charges all condense. So if these half charges condense, then they Higgs out the gauge field. We don't have to worry about the gauge field anymore. If the half charge is condensed, then the multiple charges will also be condensed. So in the superfluid, roughly speaking, what you have is e to the I theta is not equal to 0, and e to the I phi is also not equal to 0. So that's just everything condenses. Okay. Now in the trivial insulator, the half charges are not present, but you do have integer charges floating around. And so really you should think of that phase as where the gauge fluctuations are so strong that they completely confine away the half charges, and the integer charges are free to move. So this is the phase where everything is 0. And plus confinement. So the gauge forces are so strong that the half charges get bound, and you only have the phi charges that are allowed to move. Okay. So how should I think of this insulator with topological order? Well, one way to think about it is just imagine that this charge 2 Higgs field has condensed. So this is a phase where, roughly speaking, e to the I phi is not equal to 0. But e to the I phi, e to the I theta is equal to 0 in this continuum limit. Here phi, capital Phi, is not equal to 0. Okay. Let's see.
Sorry,
Yeah.
so far behind.
Yes.
I would guess that if the two objects are non-zero,
Yeah.
with my terminology, this would have been a trivial insulator.
That's a superfluid.
That's why I'm confused.
Well,
What's the low energy spectrum?
well, so there is a combination. There's a Goldstone mode associated with a combination. So there's a boson operator, which you can write down, which is e to the I phi, e to the minus 2I theta. That's gauge invariant. And so that's also non-zero, and that has a Goldstone mode associated with it. That's why this is a super.
What's the global symmetry that is spontaneously broken?
That's the one associated with this charge, phi minus 2 theta. So there is a global symmetry here, which is phi minus 2 theta. That's the physical boson operator. Yeah.
Massless?
Yes, yes. Right? Okay, there's a global symmetry, and when both of them condense, this is also condensed. So B is also not 0. That's the physical boson operator. And so there's a Goldstone mode associated with that.
There's no, okay, I'll ask it differently.
Yeah.
You can add to the the Hamiltonian, a term proportional to the cosine of cosine of the phase.
Cosine of this combination. Sure,
So there
sure.
must be that. So that would explicitly break that symmetry.
Yeah, you're not allowed to add that.
So you exclude that term.
That's right, you're not allowed to add that. So that's the global U1 symmetry of the original Hamiltonian. Okay. I'm sorry. How much time do I have? I think I need 2 minutes. Okay, saved by the bell. I prepared all this stuff, and I'm realizing it's not something that it's easy to explain, although it seemed. So let me try at least. Just what happened there? Oh, okay. So luckily I have the next. Oops, what did I do? No, you can bring it down. That's all right. You can bring it down. Yeah. All right. Let me see. Okay. Yeah. This analysis requires particle holes, a duality transformation. Okay. Let's see. So this is what I just showed you, and this is the gauge invariant boson operator, which condenses in the superfluid phase. So now what happens when we are in the confining phase? So sorry, in the phase with Z2 topological order. So I guess the easiest way to think about it is that all right, I'm going to have to reboot, but let me just give the answer now in a more technical term. Yes.
Just one question.
Yeah.
If you added in a external gauge field,
Yeah.
where would it couple here? Capital A.
It will couple over here with the -1/2 capital A. Yeah, that's right. Yeah. Okay. So okay, since I have only 2 minutes, let me try to explain this best as I can now, and then next time I will clean all this up. I won't sleep very much tonight, but that's all right. Okay, so you can further simplify this, and that will maybe make things a bit clearer for some of you. So we have this, just imagine that we have this strong, these gauge field here, which is, things really depend upon what it is modulo pi, because when I shift A by pi over here, nothing changes, but I shift A by pi over there, it changes a lot. So let's imagine we can take this gauge theory and replace the gauge field by only two possible values, 0 or pi. And similarly, e to the I phi r, I can replace by essentially 1. So I imagine that the Higgs field is basically fixed. So yeah, maybe this is what I want to say. So we're in the Higgs phase where this phi field is condensed. So we're just going to fix it. And this cosine 2a mu, I'm going to replace it by two possible values, 0 or pi. And then what you see there is that the 0 or pi values over here act like a gauge field, a field tau z that only take two values, plus or minus 1, times cosine of delta theta r. This term just disappears completely because everything is either, is basically 1 when this is 0 or pi. But this term is still present. So this is like a product of taus around a plaquette. So, and then there can be quantum fluctuations in tau, which are the conjugate of this tau z. So in this way, I've written it as in terms of a matter field for this half-charge boson coupled to what's called a Z2 gauge theory. And the deconfined topologically ordered phase is the deconfined phase of the Z2 gauge theory. Okay, maybe I'll just leave it there. Clearly, my original plan was to derive the topological quantum field theory after doing boson vortex duality, which is what this is here. But I haven't explained boson vortex duality, so maybe that's what I'll start with next time and give you a better understanding of the phase diagram of this action. All right, thanks.